Chapter 12, Stoichiometry. Section 12.1 is the arithmetic of equations. Here's our objectives. Be able to explain how balanced equations apply to chemistry and everyday situations. Interpret balanced equations in terms of moles, particles, mass, and volume. And identify the quantities that are conserved in chemical reactions. If we talk about a chemical equation, it's simply a recipe that kind of gives us a formula for how to put things together. Looks like I lost a few words there. Take a look at page 354 and you'll see the tricycle example. And what you'll see in there is that, to make the trike, you need a frame, a seat, 3 wheels, handlebars, and 2 pedals, and you get the trike. Well, when we're talking about chemistry, a chemical equation tells us how much of each reactant we need and how much of the product is formed. Just like the tricycle example told us what we needed. We needed 3 wheels, we needed 2 pedals, and so on. In a chemical reaction, it tells us, hey, we need 2 molecules, or 3 molecules of this, and what we're going to get formed. And when we do those kind of calculations, that's what we call stoichiometry. Okay, so that's what this chapter is. So basically, this chapter is about calculations, doing the calculations with a chemical formula, and this kind of puts everything together that we've done for the last 4 or 5 chapters. All right, let's take a look at this example. And this is pretty basic, and I understand that, but you're trying to get the idea of how they want you to do this. And it says, in a 5-day work week, Tiny Tyke is scheduled to make 640 tricycles. How many wheels should be in the plant? Well, obviously we know, okay, it takes 3 wheels per tricycle, 640. We know we're just going to multiply by 3, but let's do it in factor label method. Basically, what I want you to understand, okay, here's our equation. That's out of the book. Here's my relationship. What I'm saying is 3 wheels are needed for 1 trike. And I could set it up with 3 wheels on top, or I could set it up with 3 wheels on bottom. It just depends which way I want to do it. Well, what we want to end up with is wheels. We want our final answer to be wheels, and we're starting with this big thing, which is a trike. And so we would set it up in such a way that the trike cancels, and I'm left with wheels. And that would give me my answer. So be aware that even though, yes, okay, you could look at that and say, oh, I'm just going to multiply by 3. This is about understanding how we set this up, because we're going to do this with chemical equations, and you need to be able to do that. Okay? So, for example, let's take a look at this equation. This is pretty common, and we'll use this one quite a bit. We've got nitrogen gas, N2, plus hydrogen, 3H2, yields 2NH3, that's ammonia. And we can look at this in terms of a lot of different quantities. So if we talked about it in terms of atoms, for instance, we could say, well, there's 2 atoms. I got N2, 2 atoms of nitrogen. I've got 3 times 2 or 6 atoms of oxygen. So I got 2 of nitrogen, or 6 of hydrogen. And then that's on this side. And then on this side, on the right side of the equation, I got 2 times the 1. So I've got 2 nitrogen there, and 2 times 3 and 6 nitrogen there. And that's good because they have to be equal. If we want to talk about it in terms of molecules, well, we could say, oh, I need 1 molecule of N2. Each molecule had 2 atoms, but I need 1 molecule. Here I need 3 molecules of H2, and I form 2 molecules of NH3. Notice that in the one up above, when we talked about atoms, the same number of atoms are on the left as on the right. Not true about molecules. Notice I have 1 molecule of nitrogen plus 3, so I've got 4 on the left, and I've got 2 on the right. I actually have less molecules on the right than I did before. These numbers, the coefficients, also represent moles. So the coefficient numbers, so here's the 1 for nitrogen, the 3 for hydrogen, and the 2 for NH3, tell me how many molecules. They also tell me how many moles. They didn't tell me how many atoms. I had to figure that out a little bit differently. From this information, I can also figure out the number of grams. I can't just look at it, and use those coefficients, but I can use the periodic table and look up N2 and say, oh, well, nitrogen's 14 and there's two of them, so 28 grams. I can say hydrogen, there's H2, and each one hydrogen is 1, so 2 times 1 is 2, and I've got 3, so there must be 6 grams of that. And over here, when I look up NH3, I know it's 14 plus 3 times 1, or 17, and there's two of those, so 34 grams. And notice that I've got 28 and 6, which is 34. So mass is in there. And the last one is volume. And we've got quite a bit of stuff here, so let's get rid of some things here. Erase this a little bit. If I'm talking about volume, remember we said that every mole is 22.4 liters. So if I say I've got 1 mole of nitrogen, I must have 22.4 liters. Here I've got 3 moles, so I must have 3 times 22.4, or 67.2 liters of hydrogen. And here I've got 2 moles, 2 times 22.4, 44.8 liters. So notice that this one isn't equal either, there's not equal on the left or the right. So moles and stuff aren't equal on both sides, or neither is volume. All right, so we've talked about most of these. We said atoms, they're the same on both sides. Molecules, they don't have to be the same on both sides. Moles, they don't have to be the same. They would be the same as molecules. The ratio is the same, in this case 1 and 3 and 2. And mass, it does have to be the same on both sides. The law of conservation of mass says that it's always going to be the same on both sides. Volume is related to moles, so it's not conserved. It's not the same on both sides. So in a reaction, what we know is the mass and the number of atoms are conserved. Well, let's think about it. Atoms make up mass. I mean, the more atoms you have, the more grams you're going to have. So yeah, of course, those would go together. So mass and atoms are conserved in a chemical reaction. Molecules, formula units, moles, volume, not necessarily. There are examples that they do come out, but it certainly doesn't have to. In fact, most of them won't. Now here's an example of where everything would come out. I've got one molecule, I get 2 molecules. But that's just I won't say it's unusual, but it's just not the norm. It doesn't mean it has to be. But we do know that atoms are going to be conserved. There's 2, there's 4 on the left, 2 times 1 and 1, 2 times 2 is 4. So those are conserved. And here's kind of just a summary of all those things. We talked about atoms, and you can see that the atoms stay the same on both sides. Molecules, and molecules don't stay the same because some molecules are bigger than others. And if we talk about 6.02 times 10 to the 23rd molecules, we have moles. And you can see that moles, the ratios of the moles is whatever the coefficients are. That's how many moles I have. That is important for you to remember. But they're not conserved. Grams, on the other hand, are 28, 6, 34 grams on both sides is what we get. STP, or volume rather, is related to moles, so they're not conserved. These two don't equal, okay? All right, so taking a look at this equation, we've got hydrogen sulfide found in volcanic gases. The balance equation is 2H2S plus 3O2 yields 2SO2 plus H2O. And interpret this in terms of representative particles and moles. So if we talk about particles, we've got 2 molecules of H2S, and we've got 3 molecules of O2. Gives us 2 molecules of SO2 and 2 molecules of water. In terms of moles, same thing, 2 moles, 3 moles, 2 moles, 2 moles. Okay? If we talk about atoms, if we wanted to get into atoms, it's going to be a little bit different. So we would say we've got 4 atoms of hydrogen, 4 atoms of hydrogen there. 2 sulfurs, 6 oxygen, 2 times 4, or 2 times 2 is 4, plus 2 more, 6 oxygens on both sides. In terms of masses, well, we would have to look these up on the periodic table. So if you kind of go over here, H2S, the molar mass is 34.1, so you have 2 moles of that. You have 3 moles of oxygen, each one's 32, so that gives you 68 and 96. On the right side, you've got 2 moles of SO2. SO2's molar mass is 64.1. You got 2 moles of water, molar mass 18. So you've got 128 and 36. And you'll see that those are both the same on both sides. That's important. Masses are always conserved. They have to be the same. This is why you have to have a balanced equation so that you can do these calculations.